Welcome to the AI Master Course, and a special welcome to our foundational module, the Python and Data Toolkit. This module is built on a simple philosophy: practicality over theory. Every lesson you're about to hear is designed to give you the most essential, hands-on skills you need to confidently tackle advanced AI topics. We'll focus 100% on the tools and techniques you will actually use. Let's begin. Module 0. The Python and Data Toolkit. We start with Lesson 0.1, Python's core syntax, or as I like to call it, speaking the language. Imagine you're about to learn how to cook. Before you can create a complex recipe, you first need to know what a knife, a pan, and a stove are, and how to use them safely. Python is our kitchen. In this first lesson, we'll learn the absolute fundamentals of the language: our digital knife and pan. Our objective is to write a simple Python script that uses variables, data structures, and control flow to process data. We'll cover how to store information, group it together, and make our program repeat actions and make decisions. First up are variables. Think of a variable as a labeled jar. It's a container for storing a piece of information. You give it a name, like name equals Alice, where we store text, which is called a string, or age equals 30, where we store a whole number, an integer. Next, we need a place to organize our jars. These are our data structures, like spice racks. When the order matters, we use a list. For example, a shopping list could be apples, bread, milk. You can grab the first item, apples, by asking for its position or index, which in programming always starts at 0. When you have data with labels, you use a dictionary. A user profile dictionary might look like name equals Alice, age equals 30. Here you don't use a position, you use the key. To get the name, you just ask for the name key. Finally, we need the recipe itself. This is our control flow. The most important step is the for loop. It lets you say, do this for every single item in my list. For our shopping list, a loop could print, I need to buy apples, then I need to buy bread, and so on. The other key part of our recipe is the if-else statement. This is how our program makes decisions. If the user's age is greater than 18, print, you are an adult. Otherwise, print, you are a minor. A fantastic way to put this all together is with a short practice exercise. The goal would be to create a list of dictionaries where each dictionary represents a person with a name and age. The list should have at least 3 people, with one being a minor. Once that data structure is built, the solution is to write a for loop that iterates through your list. Inside that loop, a simple if statement checks each person's age. The code would then print a custom message for each person stating whether they are an adult or a minor. To truly solidify this, we can tackle a small assessment. Let's say you're given a list of numbers. Data equals 15, 22, 8, 30, 41, and 12. The challenge is to write a script that calculates the sum of only the numbers greater than 20. The ideal solution would look like this. First, you'd create a variable called total and set it to 0. Then you'd start a for loop to go through each number in the data list. Inside the loop, you'd have an if statement, if number is greater than 20. If that's true, you add that number to your total variable. After the loop is finished, you simply print the final total. The script would correctly output, the sum of numbers greater than 20 is 93.
Now that we've learned the basic grammar, let's move to Lesson 0.2 and pick up our first power tool, Pandas, the ultimate data organizer. Raw data in the real world is messy. It often lives in spreadsheets or CSV files. Pandas is a Python library that lets you load this data into a powerful, table-like structure called a data frame. Think of it as giving Python its own version of Excel, but one you can control entirely with code. Our objective here is to use Pandas to load data from a CSV file, inspect it, and perform basic data selection and filtering. A data frame is just like a spreadsheet table with rows and columns. The workflow is always the same. First, you import the library with the command import pandas as pd. Then you load your data. For example, df equals pd.readcsv, your file.csv. That df variable now holds your entire data table. Once it's loaded, you inspect it. df.head shows you the first 5 rows, just to see what it looks like. df.info gives you a technical summary of the columns and tells you if any data is missing. Selecting the data you need is key. To grab a single column, you use df column name. To filter rows based on a condition, the code is beautifully readable. df, where df column name is greater than 30. This line literally means, show me the data frame where the value in the age column is greater than 30. A great hands-on activity is to find a simple CSV file online, like the famous Titanic dataset. You'd then write a script to load it into a Pandas data frame. You'd use .head and .info to inspect it, and then practice selecting just the age, sex, and survived columns. Finally, you'd practice filtering by displaying only the rows for passengers who are older than 50. For an assessment, imagine you have a data frame loaded with columns for product, price, and category. To select and display only the product and price columns, the correct line of code is print df product price. Notice the double brackets. To filter the data frame to show only electronics, the code would be electronics df equals df, where df category equals electronics. We can organize data, but what about high-speed math? That brings us to lesson 0.3, NumPy, the high-speed calculator. Pandas is fantastic for organizing data, but for the heavy-duty math required by AI models, we need a tool that is lightning fast. That tool is NumPy, which stands for Numerical Python. It gives us a special object called a NumPy array. It looks like a Python list, but it's vastly more efficient for mathematical operations. In fact, Pandas is actually built on top of NumPy. Our goal here is to use NumPy to create arrays and perform fast, element-wise math. So why not just use Python lists? 2 reasons: speed and vectorization. Vectorization is the key concept. It's the ability to apply an operation to an entire array at once without writing a for loop. The code is cleaner and much, much faster. For example, to multiply every number in a list by 2, you'd have to write a for loop. With a NumPy array, you simply write my array times 2. That's it. This elegance and speed is why NumPy is the foundation for scientific computing in Python. To really feel the difference, you could create 2 Python lists of numbers. First, you'd use a for loop to add the corresponding elements together. Then, you'd convert those original lists into NumPy arrays and simply add them together with a single line of code. Array 1 plus array 2. The result is the same, but the NumPy code is far simpler. For a final assessment of our toolkit, imagine you have a NumPy array called prices. To calculate the final price of each item after adding a 20% tax, you don't need a loop. The ideal answer is a single vectorized line of code. Final prices equals prices times 1.20. And with that, you have now built your toolkit. You can speak the basic language of Python, you can organize data with Pandas, and you can perform high-speed calculations with NumPy. You now have the foundational skills required to stop focusing on the code itself and start focusing on what that code can do. You are ready to begin Module 1.
Module 1, Foundational Skills for AI. Welcome to Module 1. You've built the foundation. Now we formalize it in the context of real AI projects. In Lesson 1.1, we'll refine our Python programming for data science. In AI, Python is the universal glue that connects ideas, data, and powerful libraries. Our objective is to master the patterns you'll use daily to prepare data for machine learning models. We'll focus on functions and the core idea of object-oriented programming, or OOP. You don't need to be a developer, but you must understand the concept. Every AI model you use from a library is an object. The library provides the class, the blueprint, like linear regression. You create an instance of that class, your specific model, and then you use that object's methods, its built-in functions, like .fit to train it. A typical assessment here would be to write a Python script that processes a small CSV file, calculates some basic statistics, and outputs a clean result, demonstrating file handling, loops, and data manipulation, all in one. Next, in Lesson 1.2, we cover the essential mathematics for AI. If Python is the language we use to instruct the computer, then mathematics is the language the computer uses to think. Our goal is not to solve complex proofs, but to build intuition. Think of it this way. Linear algebra is how AI organizes data. A vector is just a list of numbers representing one data point, like a single row in a spreadsheet. A matrix is a grid of numbers representing your entire dataset. Calculus is how AI learns. Think of your model's error, how wrong it is, as a giant hilly landscape. The derivative tells us the slope of the hill where we're standing. The gradient is a vector that points in the direction of the steepest uphill path. To find the lowest error, the bottom of the valley, we simply take a small step in the opposite direction of the gradient. This process is called gradient descent, and it's how nearly all deep learning models learn. A key assessment of this concept would be to explain how these ideas are used. The ideal answer is this. A dot product combines an input vector of data with a weight vector to calculate a weighted sum, a key step in a neuron's calculation. A gradient represents the direction of steepest increase in a model's error. We move in the opposite direction to find the minimum error and make the model more accurate. We round out this module with Lesson 1.3, a deeper dive into data manipulation with NumPy and Pandas. 90% of a real-world AI project is cleaning and preparing data. Mastering this is non-negotiable. This involves getting comfortable with the full Pandas workflow, importing data, inspecting it with .head and .info, selecting columns and filtering rows. Crucially, it also means cleaning the data, finding missing values with .isNull.sum, and handling them, either by dropping the rows or filling the gaps with a logical value, like the average. An ideal assessment would be to take a messy data set and write a script that correctly identifies and fills missing values, and then performs a filtering and aggregation to answer a specific question, like, what is the average price for products in the electronics category?
Module 2, Core Machine Learning Concepts and Algorithms. Welcome to Module 2. We've prepared data, now we'll teach the machine how to learn from it. We begin with Lesson 2.1, an Introduction to Supervised Learning. Imagine you have a massive photo album and you want to teach a child to identify cats. You'd point to a picture and say, "This is a cat." You are providing labeled examples. This is supervised learning. We give the AI data that already has the right answers, and its job is to learn the rules. There are two main types. The first is classification, where we're predicting a distinct category. Is this email spam or not spam? The key algorithm here is logistic regression. The second type is regression, where we're predicting a continuous number. What will the price of this house be? The key algorithm here is linear regression. An assessment would involve training a logistic regression model to classify data, perhaps predicting whether a customer will churn. The ideal answer would report the model's accuracy and, more importantly, interpret a coefficient, explaining that a positive coefficient for monthly bill means that as the bill increases, the model's predicted probability of churning also increases. In Lesson 2.2, we tackle model evaluation and overfitting. You've built a model, but how do you know if it's any good? Accuracy alone isn't enough. We need better metrics, like precision, which measures the cost of a false positive, and recall, which measures the cost of a false negative. More importantly, we must avoid overfitting. This is when a model learns the training data too well, including its random noise. It's like a student who memorizes a practice test but then fails the real exam because they didn't learn the actual concepts. The goal is to find the sweet spot between a model that's too simple and one that's too complex. A crucial assessment question is to explain overfitting and how to fight it. The ideal answer is, overfitting is when a model fails to generalize to new data because it memorized the training data. Two ways to reduce it are 1. Use more training data, and 2. Use regularization, a technique that penalizes model complexity to discourage it from learning noise. What if you don't have the right answers? That brings us to Lesson 2.3, Unsupervised Learning. Here, you just have a mountain of raw data and you want to find hidden structures. The two main tasks are clustering, which automatically groups similar data points together, and dimensionality reduction, which reduces the number of columns in your dataset while preserving important information. The key algorithm for clustering is k-means, and for dimensionality reduction, it's principal component analysis, or PCA. A great assessment for this is to use PCA to reduce a dataset and explain why. The ideal workflow would be to take a dataset with many features, apply PCA to shrink it to just 2 components, and then plot the result. The explanation would be, I did this because the original data had too many dimensions to visualize. By reducing it to 2D, I can now see the data structure and identify potential clusters, all while retaining most of the original information.
Module 3, Introduction to Deep Learning. Welcome to Module 3. We're now ready to explore neural networks, the engine behind the modern AI revolution. In Lesson 3.1, we cover neural networks fundamentals. For incredibly complex patterns like recognizing a face or understanding language, we need an approach inspired by the brain. Neural networks stack layers of analysis on top of each other, allowing the model to learn increasingly abstract features. They are made of neurons organized into an input layer, hidden layers, and an output layer. Deep learning simply means a network has many hidden layers. The key to their power is a component called an activation function, which introduces nonlinearity, allowing them to learn patterns far more complex than a straight line. They learn through a process called backpropagation, where the network makes a prediction, checks its error, and then works backward to adjust its internal weights to be more accurate next time. The assessment here is to explain these core components. The ideal answer: an activation function introduces nonlinearity, letting the network learn complex patterns. Backpropagation helps the network learn by calculating the prediction error and then propagating it backward to determine how to adjust each weight to minimize that error. We don't have to build these from scratch. In Lesson 3.2, we learn about building neural networks with TensorFlow or PyTorch. Think of these frameworks as incredibly sophisticated Lego kits for building AI. They provide pre-built, optimized components that we stack together. The workflow is standard. You define the model by stacking layers, you compile it by choosing an optimizer and a loss function, and then you train it by calling the .fit method on your data. A typical assessment is to build and train a simple network to classify the famous MNIST dataset of handwritten digits. The ideal answer would include the code to define, compile, and train the model, and would end by reporting the final test accuracy, for example, test accuracy 97.5%. Finally, we look at a specialized architecture in Lesson 3.3, Convolutional Neural Networks, or CNNs, for image data. A basic neural network struggles with images because it loses all spatial information, the fact that pixels are next to each other. A CNN is designed to see like we do. It uses convolutional layers with filters that slide across the image to detect small features like edges and textures. Then, pooling layers shrink the output, which reduces computation and makes the feature detection more robust.
After many such layers, the extracted features are fed into a standard neural network for the final classification. The assessment is to explain the roles of these layers. The ideal answer? Convolutional layers use filters to scan an image and create feature maps that detect patterns. Pooling layers then downsample these feature maps, which reduces complexity and helps the network recognize a feature no matter where it appears in the image.
Module 4. Applied AI and Project Work. Welcome to Module 4. True proficiency comes from building. Here, you'll integrate everything into practical projects. Lesson 4.1 covers the end-to-end machine learning project workflow. A real project isn't just a single line of code, it's a structured process. It starts with defining a business objective, then comes data collection, followed by data preparation and cleaning, which is often 80% of the work. Only then do you select, train, and evaluate your models. The final step is to evaluate your best model on unseen test data and present your results. A capstone assessment for this is to choose a data set from a site like Kaggle and complete a full project documenting each step. The presentation would sound something like this. I chose this data set to predict customer churn. I handled missing values by filling them with the median. I selected a random forest model because of its robustness. On the final unseen test set, the model achieved an F1 score of 0.85, indicating a strong balance between precision and recall. In Lesson 4.2, we learn a powerful shortcut, leveraging pre-trained models and transfer learning. Training a state-of-the-art model can take weeks and thousands of dollars. You don't have to do that. With transfer learning, you take a model that experts have already trained on a huge data set and you adapt it for your own smaller task. You're not starting from scratch, you're standing on the shoulders of giants. The workflow involves loading a pre-trained model like ResNet 50, freezing the early layers to keep their knowledge, adding your own new classification layers on top, and then training only those new layers on your data. It's dramatically faster and more effective. The power of this technique is obvious in an assessment. A student would show that their own custom-built model achieved, say, 65% accuracy on a small data set, while the fine-tuned, pre-trained model achieved 95% accuracy in a fraction of the training time. We then turn to one of the most valuable data types in Lesson 4.3, an Introduction to Natural Language Processing, or NLP. This is the field of AI dedicated to understanding human language. The first challenge is always turning words into numbers that models can understand. This is called vectorization. State-of-the-art models like BERT create powerful word embeddings, where the vector for the word bank is different in riverbank versus investment bank. A classic NLP task is sentiment analysis. An assessment would involve using a pre-trained model from a library like Hugging Face to classify customer reviews. The ideal script would take a new, unseen review, like, I love this product, and correctly output the prediction, positive. Module 5. Ethical AI and Next Steps. Welcome to our final module. Building powerful AI comes with an obligation to consider its impact. Lesson 5.1 is on responsible AI and bias. An AI model is a reflection of the data it was trained on. If your data contains historical human biases, your model will learn and automate those biases at scale. An AI used for hiring, trained on a historically male-dominated industry, might learn to unfairly penalize female applicants. Developing AI isn't just a technical challenge, it's an ethical one. An assessment for this critical topic would be to propose a method to mitigate bias in a loan approval AI. A strong answer would be, first, I would audit the training data for balanced representation across demographic groups. Then, I would evaluate the model's error rates separately for each group. If bias is found, a mitigation strategy would be to reweight the training data to give more importance to underrepresented groups and then retrain the model, aiming for equitable performance. This brings us to our final lesson, continuous learning and specialization. Congratulations, you have completed the accelerated path to AI. But this field evolves at an astonishing pace. The most important skill is learning how to learn. This means reading research papers, following key people and labs on social media, contributing to open source projects, and above all, to keep building. Your final assessment is personal. It is to create your own AI learning roadmap for the next 6 to 12 months. A great plan would be specific and actionable. My goal is to specialize in NLP. For the first 3 months, I will complete the Hugging Face course and fine-tune a BERT model. For the next 3, I will read the original Attention is All You Need paper and build a simple transformer from scratch. In the final 6 months, my goal is to make a small contribution to an open-source NLP library. You have successfully navigated the accelerated path to AI proficiency. You started with the fundamental tools, mastered core machine learning paradigms, built deep neural networks, applied your knowledge to projects, and considered the ethical responsibilities of your work. You are now equipped not just with knowledge, but with a framework for continued growth in this incredibly exciting field. The journey is never truly over. Keep learning and keep building.